Hello everyone, welcome to the virtual talk on the study titled on Tribology Aware Deep Learning Based Digital Twins for Automated Maintenance of Subsea Oil and Gas Components, authored by me, Prathamesh S. Desai, and co-authored by Victoria Granha and Fred Higgs. Here is a brief overview of my talk. I'll start by introducing the problem encountered in the maintenance of subsea oil and gas components and lay an objective which we are trying to achieve in this study. Then we will delve into the methodology which we have come up with to achieve this objective. I'll spend some time in describing the tribological experiments that were conducted in this research and the digital twin that was developed to perform predictions about maintenance activities. I'll end by presenting the results and summarizing the findings. Here's a quick schematic of a typical subsea oil and gas field where the production platform is located hundreds of feet above the seabed, where oil and gas are being extracted by various systems and being pumped up into a storage ship which brings oil and gas back to the shore. The problem which oil and gas producers are facing is that oil and gas prices exhibit high fluctuations. And while trying to meet these low selling prices, oil and gas producers can go bankrupt. Maintenance of subsea components is expensive, and this opens up an avenue to cut costs. And there is a way, but to do that by optimizing and automating the maintenance of these components. So if we look at the entire oil field, we can come up with a hierarchy of digital twins, which can be useful for a typical oil and gas field. If the digital twin looks at the entire plant, it's a plant level digital twin. A level below that is a digital twin that looks at different systems. It's a system specific digital twin. For example, it can be a digital twin for a manifold or a sucker pump. And at the bottommost level is what we call our component level digital twins. Now these are digital twins of the components like gears, bearings, balls, which can be brought together to form a system, and all the systems can be brought together ultimately to create the plant level digital twin. This study is going to focus on component level digital twin. Now when we look at the literature for digital twins in maintenance, first of all, in digital twins to begin with, there is not a clear-cut definition out there. Kritzinger and others have come up with a good way to define different connectivities between physical object and a digital object. What they're saying is if the two objects or the two entities are not automatically connected, or there is no automatic data transfer, two-way data transfer between these two, then it's a simple digital model or a simple computer simulation. We ourselves have called this previously virtual avatar. And sometimes these digital models are confused as digital twins, but in reality they are not. And if the digital object is able to automatically evolve or learn from the data coming out of the physical object, then these this category of models will be called digital shadow. And finally, you have the holy grail, where there is a two-way automatic data flow between the physical object and the digital object. And only if you have such a connectivity, then what you have developed is a digital twin. There is still a confusion about digital twins, and sometimes a digital shadow is reported as a digital twin. I thought so just because we are at a digital twin conference, it might be a good place to lay down this terminology which is out there. And then if we look at digital twins in maintenance, maintenance can be broadly categorized into two types: a reactive maintenance strategy or a proactive maintenance strategy. Reactive is essentially saying do not do anything till the system fails, and when it fails, do the maintenance. This is not such a wise way of performing maintenance. Proactive can further be categorized into four increasing levels of smart maintenance systems. The very first on that list is routine maintenance. No matter what, after a few hours of operation, perform maintenance. This is preventive maintenance. A level above that is look at the condition of the assets, and if they require maintenance, then do maintenance. That is condition-based maintenance. Now, if this decision making is performed by a computer model conducting statistical analysis, then it becomes predictive maintenance. And the topmost or the holy grail in maintenance is prescriptive maintenance, where you're not only telling when to do maintenance activities, but also describing some other things which can be done to improve the overall life of your equipment or component. This is adapted from Erandonia et al. Now, the present study lies somewhere in between a digital shadow and a digital twin. The model which we have developed is in principle a digital twin. It just hasn't been deployed in field. And we think of it as being predictive maintenance. So this brings us to the objective of the study. It is to develop an AI-based digital twin framework for tribological components in subsea oil and gas. Now let's look at the methodology which will help us to achieve this objective. It's a 3-pillar approach where the 3 main things which we'll look at are experiments, data processing, and then finally in the digital twin architecture. Experiments in this case involve performing accelerated deterioration tests. Then we collected sensor data and measured wear scar. And based on the wear scar measurement, we calculated what is called as RUL, that is the remaining useful life of that component. And as usual, there is some data processing where you trim in, running in, and post seizure data, and split the data sets into training and test data sets. Then on the digital twin side, we need to come up with an architecture. In our case, we have come up with a convolutional neural network architecture. It can be any other architecture. Then conduct model training and testing, and if we have achieved the desired accuracy, deploy the digital twin in field. The tribological experiments which were carried out in this study made use of a benchtop 4-ball test apparatus shown on the right, and it's designed to simulate typical ball bearings, or in this case subsea ball bearings. The lubricant used was a commercial lubricant oil used for subsea components. What happens in this test is there are 3 balls held in place in this ball pot, and there is lubricant oil filling the ball pot. This thing is loaded from the bottom, and the top ball, the 4th ball, rotates at high speed, and you examine the evolution of wear scar with time and determine what is the lifetime performance of the lubricating oil. If we unpack this further, the schematic looks something like this, where the top ball is rotating at high speed and bottom 3 balls are held in place, but are held in place with some load. After the test, if we look at the 3 balls from top, we are able to see 3 small wear scars. This can be examined using a microscope, and a typical wear scar looks like this, and you go in and measure principal and major and minor axes diameter length, and based on that you're able to figure out the average wear scar size. And if there is a predetermined failure size, which in this case we fixed it as 2 millimeters, with respect to that you can then back calculate what is the remaining useful life in this tribo system. Now, this particular chart shows interrupted wear scar measurements and resultant RUL life. This is remaining useful life of the tribo system. It's quite an informative chart, and I'll go through it in a slow fashion. Y-axis on the left is showing frictional torque measurements. Y-axis on the right is showing RUL calculations. X-axis is time, and also shown is temperature evolution with time. Continuous red line is frictional torque, and connected blue dots are RUL calculations. When the test starts, there is a sudden rise in friction, and we call this period as the run-in period. And starting with no scar diameter, wear scar is developed when it reaches into near steady state operation, and the wear scar is almost like a nice circular wear scar. This is the shadow, this is the wear scar. You can see how the wear scar evolves. It stays almost constant, and then beyond a certain time there is this high rise in frictional torque, and it results in incipient seizure. And beyond this, the wear scar looks very big, rough, and it has lost its circular shape as well. So the wear scar suddenly increased from 500 microns to 1500 microns. So this is a highly non-linear change, where it was initially almost flat, the RUL was almost flat, and then there is a sudden decrease to 20% of the useful life. We are trying to develop a digital twin which can predict this based on various sensor data gathered by the equipment. I'll talk about different sensor data in my results section. Okay, so going ahead, the digital twin developed in this particular study is a convolutional neural network. Before I describe the digital twin, we'll have to spend some time in understanding different types of convolutions. Now, regular convolutions are where you have an input vector and subsequent hidden layers are looking at input data not only in the past but also in the future if this is an increasing time. As you can imagine, this is not a good type of convolution for time series data, because subsequent hidden layers are looking at not only the data in the past but also in the future, so that is considered cheating. So to remove this problem with regular convolutions, what we have are known as causal convolutions, where you look at data only at time steps before the time step of interest. These are causal convolutions, and a level above that is what is known as dilated causal convolutions, where in between data points are skipped so that subsequent hidden layers can look at a much longer input string when compared to causal convolutions. We have used dilated causal convolutions in our study. The architecture of the digital twin is shown in this figure. It's essentially a multivariate convolutional neural network, CNN, with dilated causal convolutions, where input is a matrix comprising of window size by features being sensor inputs or sensor outputs, and the output is remaining useful life at time t plus 1. If this was from 0 to t, then at time t plus 1 is your RUL, and you slide the window across the entire time series. Now, in between, you have dilated causal convolutions with ReLU activation function, flattened layer, and a dense layer. Performed various topologies of neural network were tested, where window size was varied from 16 to 128. Number of kernels tested were 64 and 128. And number of neurons in the dense layer were 128 and 256. All the other parameters were kept constant. Coming to the results, the sensor data which was gathered in this study comprised of frictional torque, load, and temperature. And then the final RUL chart is calculated based on wear scar measurements. The best performing digital twin architecture was architecture number 9, which had a window size of 64 filters were used, and dense layer had 128 neurons. So the total number of trainable parameters was almost 567,000. Training time was 3 minutes 18 seconds, and training accuracy R was 99%. Test accuracy was 95.3%. I have also reported mean absolute error for training and testing. So what was done was, since we had limited amount of data and these experiments are a bit expensive to conduct, we iterated through different data sets, assuming some to be used for training and the remaining to be used for testing. So to be more specific, we conducted 3 4-ball tester tests, and we iterated through these tests. So in this case, what I'm showing is a digital twin trained on experiments number 2 and 3, but tested on experiment 1, and we'll iterate through. The next one will be trained on tests 1 and 3 and tested on 2, and so on. So here, the trained digital twin was tested on experiment number 1, and the connected black dots are the predictions from the digital twin, which was trained on these two. So you can see the training accuracy is pretty good, but testing here, there is a delay in the onset of a sudden decrease in RUL, at least for this particular data set. Then when the digital twin was trained on experiments 1 and 3 and tested on 2, we saw that the onset of sudden decrease in RUL was correctly predicted. However, there was a region preceding to that onset where the digital twin thought that for some reason the RUL is increasing, which is not physically correct. And this is the final iteration where now the digital twin is trained on experiments 1 and 3 but tested on experiment 3. Here the training is not that good for 1, but it's good enough for 2. And testing is also test results are also pretty good. There is a lag in between the sudden drop, but once it does, it's able to capture that sudden decrease in RUL in a very efficient manner. So we think once we have this digital twin, now this can be deployed in field where it can continuously look at different streams of data, such as frictional torque, temperature, normal load, and can throw a flag that a particular component needs maintenance because the RUL has gone under a certain user-defined value, which can be 30% or 20%. That's a user-defined input. So to summarize, automated maintenance of subsea components can help to improve the efficiency of oil and gas producers. Sensors can be used to extract tribological data. Predictions about RUL can be made by monitoring the sensor data. In our particular case, we developed an AI in the form of multivariate convolutional neural network to perform these RUL predictions. The AI can now be deployed in field to guide automated maintenance. Now, the findings of this study have been published in the Journal of Processes. The manuscript details are shown here. All right, thank you. And if you have any questions, please feel free to contact any of the co-authors. The contact details are given here. Thank you.